Sorry, I'm not prepared.
No, my apologize to all the people here. But I would like to try to give the essential.
Yeah, perfect. Okay, so then let's start. This is second talk of this last day of the conference, and the speaker is Jean-Jacques Szczeciniarz.
Yes.
And he's going to talk about remarks on Penrose integral transform.
Yes.
Thank you. You can go.
Okay. Okay. No, this talk is after my meeting with Claudio, and we was at the colloquium in Roche-Rachel. And it was a colloquium about mathematics, fields of mathematics, and history of mathematics. And we discussed, Claudio and me, about philosophy of mathematics. And this discussion last now, and I have to thank many thanks to Claudio for his orientation and for his philosophical orientation, mathematical and philosophical orientation. My topic will be essentially about Penrose and Roger Penrose and his mathematics and physics and his philosophy. And it will, for me, be the opportunity to explain what is my point of view about philosophy of mathematics. Now, philosophy of mathematics for me, and it is very difficult to explain this point of view, for me is internal, inside mathematics. And for this reason, I cannot agree with official philosophy of mathematics and particularly analytic philosophy of mathematics and so. In my view, philosophy is acting inside of mathematics, not always explicitly, but implicitly, and this philosophy deal with some very difficult topic in history of philosophy, but inside of mathematics. For example, it is the question of what is finiteness, what is finitariness. It is a very big question. For example, in the case of Penrose, what it means, the act of compactify. And compactify is the act to make finite some object in the geometry or in physics. And my essential topic will be maybe more paradoxical in this sense that I will present you some very will be pedestrian computation and in detail computation inside the mathematics of Penrose and inside some theory of Twister, etc., etc. But in my view, this presentation, this computation, this calculation may be pedestrian calculation, computation are object for philosopher also. And for me, it's very important in this sense. I will repeat the other topic in the Penrose. Penrose said that the secret of nature lies in the complex number. And he says that he speak about some, to say, holomorphic ideology. And it is a philosophical point of view also. So, I will make two topic in introduction. In a formal presentation of my talk, in the sense is mathematical talk, and more concrete presentation. Formal presentation is about Penrose transform, and this Penrose transform is very close to Fourier transform, and for the Fourier-Mukai transform, and the core idea in the definition of an integral functor is in this sense. If we have two varieties x and y, we can take some object on x, pull it back to the product x, product y, twist him by some object kernel in x time y, and then push it down, integrate on x. And the more concrete example of this process is the Fourier transform on function. A little more concretely, I can present a general frame of the Penrose transformation, and it will be some computation for you, and we are not for you is some trivial calculation, but for me it's very important that we have this pedestrian computation. And it will be the presentation of the works by Gindikin and Henkin. And Gindikin and Henkin give the survey of the presentation of solution of a system of massless equation in terms of the Cauchy-Riemann equation of the space of Penrose twister. That is more concrete. And in this frame, the Penrose transformation is investigated by means of complex integral geometry. It is the frame of the integral geometry by the leader of this conception was Gelfand, and team by Gelfand, and it was Gindikin and Henkin. And then other people like Shabbat, and then other people in the team of Paris 7. So I can give this example because it's very simple. Suppose that a hyperplane N specific the condition that permits Z equal to 0, the surface of loose twister. The set of complex lines lying on N is then taken as M. The group of projective transformation preserving N is isomorphic to SU22, and then induce automorphism of M together with the conformal class of metrics associated with the intersection of lines. We will see in a little more detail this situation. I can go more concrete. Considering N minus L is a fixed line, and the line lying in N minus L arrive at non-compactive in Minkowski space 0 and null, and the group of automorphism of n minus 1. And then M0 is isomorphic to the Poincaré group. Points of n can be interpreted as a light right isotropic line on n. I will go in detail in this topic. So, what is very important in this topic of this presentation for me is you have a mechanism of mind, some sort of mental mechanism. And mental mechanisms are a step of mathematization. And this step of mathematization are important, and we can think about this step. The first step will be in the spirit of Penrose, complexification. And we'll see what it means, complexification. The second spirit, and we will see the second topic, see more in detail, is the compactification. So you have complexification and compactification. And compactification is, from my point of view, some sort of deep philosophical reflection about finiteness. Because compact is the finitely topology. And what it is some sort of reflection on the sense of finiteness through the compactification. So we can see more in detail, more simply, first of all, complexification on Minkowski space. You know that space-time introduced by the German mathematician Hermann Minkowski is the four-dimensional real space M of the point X, provided with the hyperbolic metric, you know, X0 represents time, and the remaining coordinates are spatial. And it is the frame of the theory of relativity. According to fundamental postulate of this theory, the velocity of a signal cannot exceed the speed of light, c, which is taken to be normalized equal to 1. The equation norm square equals 0 defines a cone in M, which is the light cone whose vertex is x0. Its interior is so described and is split in two naps for which x0 greater or less than 0 respectively, and the respective so-called future cone and past cone. They consist of alpine widths with which the point x0 can communicate in the future or in the past according to the above postulate. Now, communication is impossible with points outside of these cones. So in contemporary mathematics has arisen the need of a complexification of the space. And Penrose is right. All the frame in the physics mathematics contemporary is a complex number. It's inside a complex number. So this means an embedding into C4 as a real subspace here 4, and the completion by point Z is X plus Y, for which you have this inequality according to the same postulate. And you have the tube over them, and we dispose in this way the complex Minkowski space. So we need know the grid compactification, the grid compactificator, and the grid compactification in this case is the Grassmann. And Grassmannian is very important in this sense that it's some sort of realization of some finiteness compactifier. I give an analytic description of G and K, and you know this is that it is a simple linear algebra, and you have this matrix A. So the rank of which is equal to K plus 1, and if we choose another basis and to have this expression, and you have this corresponding matrix B is equal to 8C. So that is the and you have dispose G and K Grassmannian, and I will present the Grassmannian G31. It is used very often by Penrose. And in this Grassmannian, you dispose also coordinates, yeah, and this Grassmannian is manifold, and we have a cart, and we have the passage from one cart to another, etc. And you dispose also generalizity complex homogeneous coordinates, the Blücher coordinates of the manifold G and K, and the number of them is so the binomial coefficient n plus 1 by K plus 1, and you have this binomial coefficient. And we can introduce this structure as in the case of complex projective space. Complex projective space is the particular case of Grassmannian. So the Grassmannian G31 of the play of the dimension of its component, namely, it can be interpreted as a set of lines in P3 or PC3. The line will be called by Penrose twister, and we will see that twisters are very diversified, and you can use a twister in very many ways. And in physics, if we specify a line by two of its points with homogeneous coordinates, and then the coordinate Blücher coordinate would be so P mu is difference, and that means that there must be a relation between this P mu. From historical point of view, you can see a very brief remark. The Twistorian idea can be seen as coming from the complex frame of complex geometry. And the other historical origin is in physics and in Penrose's work. And that is very interesting. That's interesting that you have this idea, this topic, is together comes from complex geometry, deep in complex geometry, and from physics. And that is also point of Penrose point of view, that the unity between complex geometry and physics through Twistorian theory. So when come back to the Minkowski space, you know that the Minkowski space forms the common part of the boundary of the domain MC plus minus, and is the Schiller boundary. But one needs another ingredient, that is the Pauli transformation. And the Pauli transformation proposes that we represent point X in M by Hamilton matrix in this form, with determinant of X is norm square. And the Pauli transformation is extended to C4 in this form. there is a non-degenerate linear transformation. It transforms the tube domain, MC plus minus, into the generalized upper and lower half plane. So where Z is this matrix representation of points of C4. And imagine excuse me. Excuse me. Imaginaire Z is this equality, pedestrian, and is an Arminian matrix, and the seeing whose equal or greater and less or equal means that it is positive definite or negative definite. And under this transformation, the space M itself goes to the set of the Hermitian matrix set for which you have Im-Z equal to 0. It is the real four-dimensional plane in included subset of C4. It is usual to not distinguish, it is not an object and their image under the powder transformation. In order to study the condition at infinity, and it is very important from my point of view, that is study the condition at infinity. It is all the history of projective complex geometry, from Desargues to comparative time. We need to compact in the space MC. Penrose proposed to do this by embedding MC in Wassmann manifold G3 with complex dimension also equal to 4. And we said that represent the plane of C4 by matrices Z, and for G3Z one takes. And the set of them will be considered as one of domain of the standard covering of G31, the affine part of this manifold. The general point of G31 are represented by equivalent class of 4 two matrices. Still, Z is this. The point of the affine part of the G31 are represented by matrices form for which determinant of Z1 is not equal to 0. And you have the point of the matrix is this as a form with tilde Z with Z is a product. Now, it's a very important point for the compactification at infinity of C4, when glues on the set of lines that are representable in the form of tilde Z is a condition that the determinant of Z1 is 0. All the process is similar to the compactification of C, I see. We add to the real space M the set of matrices for which determinant is 0 at infinity. We glue on the code from R4. No, I cannot develop my philosophical or technical mathematical remark that it is important that you have some sort of logic of the compactification, and together this reflection on the finiteness and inside the geometry. Now we have to distinguish in C4 the part M and C. The trick is to introduce the 4-4 matrix phi we consider the matrix form, this, where Z tilde is the matrix Z tilde in this form, and tilde Z star is conjugate transpose. And we use a function or a form matrix in this affine frame. In the affine frame where tilde Z has a form A Z, this form is here. For any matrix of the form tilde Z by Z, tilde is Hermitian, and its sign is not changed when tilde Z is multiplied by an generate to two matrix C. Therefore, on the Grassmannian, we can distinguish this domain, and the set is this domain. One sees from the above computation for tilde from the affine part of G3431 that these are compactification of NC plus minus. The union, so is scaled projective complex Minkowski space. The point of G31, the point tilde in G31 can be interpreted geometrically as line in P3 or two planes in C4, spanned by the column of the matrix tilde Z. In particular, for point of the affine space of the Grassmannian, represented by the matrix tilde Z, such planes are the form very well known indeed. W is lambda rho plus mu, so where W is the column vector with coordinates W0, 1, 2, 3, and lambda and mu are complex parameters. And we can rewriting this equality in coordinates. We will think that lambda is W0 and mu is W1, and then the equation of the plane takes the form is. If we take W time to be homogeneous coordinates in P3, above equation, it will be the equation of the projective line corresponding to a plane tilde Z of this form. No, and we can describe Penrose transform. The form of Penrose transform, this form is the P is Z arrow L, with L defined in this way. We remark that using the matrix form, we can introduce an Hermitian form in twistor space P3. This P3 with W, a column vector of homogeneous form. This form defines a real hypersurface N W in P3 and 12, which divides P3 in two domains, D plus minus, W in P3, with R by W greater or less than 0. And Penrose scaled the point W in D plus 1 positive and negative twistor. And to have the first theorem about Penrose transform. The Penrose transform takes points from M tilde C plus minus into lines that lie wholly in the domain D plus 1 of the positive negative twistor, and the point of tilde M into lines of the hypersurface of the null twistor. I have no time to give some detail of the proof of this theorem. This theorem is illustrated by the figure below, and you have here the bone on the M tilde. So, and P is the map with Penrose transform, and you have the line PZ tilde plus and PZ tilde and T plus in this hyperboloid. I will give some transformation to continue transform Penrose transformation describing. We need a condition for the intersection of two lines corresponding to the point of one part of GR31. From the affine part, you have the affine now represented by matrix Z and Z prime. Z is this. The intersection is that the system of analog equation with the matrix Z prime has non-zero solution. And if Z make non-equal to Z prime, the rank of the system is equal to 3. Its solution is determined of a scalar point of intersection of the line. P of Z and P of Z prime is unique. We use the previous condition. If P of Z0 is L0 to the point Z, which may correspond to the line intersecting, if an odd determinant of P is 0, and the complex hypersurface, so the space C4, is called the complex line code with vertex Z0. The two matrices for which determinant 0 are characterized by the possibility of being represented in the form, this form, this matrix and this matrix. The point of this cone admits the representation given by this equation. From this, one sees that on this cone there are two family of complex two-dimensional planes, very important in the theory. The family of alpha plane, called P beta, on which the values of beta, beta 0, beta 1 is fixed on the parameter of the variable alpha, and the family of beta plane, called P alpha, with fixed alpha and variable beta. The restriction of the Penrose transformation, the Minkowski real space is this. L contains the real line, L infinity corresponding to the point 0, the line of L.
Jean-Jacques, excuse me, perhaps you can wrap up in 5 minutes?
Please?
Yeah, if you can wrap up in 5 minutes, that would be great.
Okay.
Thank you.
I give this theorem, theorem 2, for a fixed vertex Z0, the Penrose transformation P associated some point twister in P squared to each alpha plane, and an alpha plane in P squared to each beta plane, a point of the dual space P3 star. And to have this figure here. These beta plane and these alpha plane are very often used by Penrose in these twister theories in general. I give some two theorems. Because the very important demonstration is about the Maxwell equation. And you have this theorem. In the Maxwell equation, given in the form, very simple form by this Hodge operator and differential form, you have the self-dual form and anti-self-dual form. In the self-dual forms, in the equation, Maxwell is cited by the fact that they vanish on beta plane and the anti-self-dual plane vanish on alpha plane. No. And what is very interesting for me is you can get an integral representation of the solution of the Maxwell equation. And to get this integral representation of this solution, you use the Penrose method and the Gilby-Pinant Henkin method, Kindikin and Henkin proposed to use a differential form to give this integral representation of the solution of Maxwell equation. And this computation is a little complicated, but some simple, but non-trivial. I have not the time to give completely this computation. And the theorem important also theorem is that the transform P Penrose gives all self-dual solutions of Maxwell equation, and it is some computation, and to be sure that we have all solution, that we have only this solution of Maxwell equation. And it's interesting that the method is to use fiber of P3 and to give the anti-evolution to give some reciprocal transform and Penrose transform. And the computation is also long and tedious. And you have the presentation in the book by Shabbat. It gives the complete in detail computation. And if I present this, you know that I wanted to present you first of all the Penrose transform as operator, an operator in the frame of physical mathematics, and in two forms: the form of from the point of view of object, of space, and from the point of view of operation. And from this point of view, you have the whole Maxwell equation solution, particular solution. So it is the first part that I wanted to present to you. This part is more the point of view of computation, and you get not so abstract point of view. This point of view of computation. And for me, this part is important because inside this computation, you can extract some abstract and the point of view of category theory. You can generalize, formally generalize this Penrose transform and use the Penrose transform for cohomology and for cohomology for the use of Dolbeau cohomology, and we introduce this Dolbeau cohomology, and that is the consequence of the concept of Penrose transform. I want to finish because I have no. It's important that we have in this concept of function, you have a change in the concept of function in relation to the concept of Penrose transform. The concept of function is not function, but you have the concept of correspondence. And from the point of view of philosophy of mathematics, the passage from function to correspondence is some sort of generalized abstraction of the concept of function. And it's important that you know, my project that exists many concepts of transform since Laplace, Fourier, Radon, and the general, more general, Andreotti, Norgay transform to Khaled, rho 0, and until Penrose. And we should continue the mixes of this concept. When I go to the end of my talk in this point of view, we can make some remark on the abstract transform Penrose, Penrose transform. Like Eastwood, Penrose and Eastwood, Penrose and Rendler. And I will finish with the transformation in this remark, this description. What is the Penrose transform? We have been considered some double flag correspondence or generalized flag varieties in this form. And you have seen that you have a fine frequency space induced and sub-double fibration by means of this very simple and deep structure, the Penrose transform. It's complete cohomological significance, and you have this, some isomorphism, and we can interpret cohomological point of view in this case, and can provide the reader of this mathematics, this streamlined version of this machine in the context of arbitrary semi-simple group. And we can have this basic geometric setting. And the invariant differential equation on Y will be induced by the Bernstein-Gelfand resolution, and the cohomology of homogeneous shifts on Y will be computed as section of homogeneous shifts on X using the Bode-Borel theorem. The whole construction will be manifestly invariant under the action of the ring algebra J and Bj, and under any subgroup of J which preserve the space X. And if I give the Penrose transform in principle, I can sum up the general transform Penrose in as follows: X and Y and Z are complex manifolds, and suppose you have a double fibration, and eta and tau are subjective mapping of maximal rank, and the pair eta tau embeds Y as submanifold of Z product Y. This shall be correspondence, as I said. And I will give the last mechanism of the Penrose transform. So we have the double steps. Pull back to Y in this setting. Roughly speaking, the cohomology class omega is regarded as cohomology class on Y, which is constant of the fibers of eta, and push down to X, pull back and push down. It is the mechanism, and it is very close to the first presentation, CT presentation category theory in this form. And so,
Jean-Jacques, perhaps you can conclude.
1 minute. 1 minute.
Okay.
Donc, it will be said that in philosophical reflection, roughly speaking, will be said that the Penrose transform consists of a system of anticipation of solution of differential equation corresponding to the description. The concept of transformation as realized by Penrose is manifest and basic theoretical movement. Et voici important are the two topics I will emphasize here. The concept of compactification by means of Grassmannian and compactification of projective, complex projective compactification. And the second role lied by the complex number. Complex number, say Penrose, are the secret of nature. Secret of nature. I have not the means to dévoiler this secret. For me, the complex number maybe is the best way to represent some sort of non-locality. And it's very important to have the non-locality for immediately for the quantum mechanics, non-locality. And this non-locality is amplified by homological machinery, and this non-locality will be deepened by the mathematical physics. So, complex number, complexification, non-locality, the three chapters for the philosophical reflection. Thank you, and I apologize for all the events for my talk. I hope that we are not gênés by this.
Okay, thank you very much for your talk. I'm not sure we have time for questions since we are 15 minutes late.
Yes, thank you, Jean-Jacques. It would be nice to discuss in depth your interesting talk, but as Ugo said, time is tyrannical, so we have no time to discuss. But of course, we will have time to discuss personally about that. I have many remarks. I would have many remarks, but Ugo, I think that it should be better to pass to next and
Sure. Yeah, thank you.